Hi, welcome to today's astronomy video about brown dwarfs. Brown dwarfs could become very important in the far future. This is a comparison of a brown dwarf at the left with the gas giants Jupiter and Saturn. You can see it's not so different in size. Brown dwarfs have a mass between 13 and 80 Jupiter masses. That's not enough for a fusion of normal hydrogen, protium. But it's enough to make a deuterium fusion. Deuterium is about 1 to 2 out of 10,000 isotopes, isotope nucleates. And so the deuterium fusion has a lower activation energy. That's why it is possible in a brown dwarf. Brown dwarfs are not brown. They have a reddish or a purple color. This is another comparison of brown dwarfs compared to other big objects. At the foreground you can see Jupiter. This is Earth. Bigger objects are the red dwarfs, M stars. So this is a range between 13 to 80 Jupiter masses. The metallicity is important in this context. Metallicity in astronomy means the percentage of elements other than hydrogen and helium. The brown dwarfs with a mass of above 65 Jupiter masses can fuse deuterium and lithium-7. And there are 4 subtypes of brown dwarfs, M, L, T, and Y. This was first discovered brown dwarf, Teide 1, discovered in 1995. This is an image from the Spitzer Space Telescope. You can see this a very faint object. Teide 1 is located in the Pleiades cluster, 400 light years from Earth. The M-type brown dwarf mass is between 40 and 70 Jupiter masses. Its age is about 100 million years, and its surface temperature 2600 Kelvin. So there are 3000 known brown dwarfs. They are difficult to detect because they are very faint, and there could be potentially billions in the Milky Way galaxy. This is another brown dwarf, Gliese 229b. This is a companion of the M dwarf Gliese 229, which is located at 19 light years distance. The M dwarf has a mass of 58% of the Sun. The brown dwarf Gliese 229b is a T-type dwarf, which is located at 29 AU from the parent star. 1 AU is the Earth-Sun distance. Its mass is 60 Jupiter masses, orbital period 247 years. And the system could also contain a super Neptune and a super Earth. And this was the first image system of a brown dwarf. This is how the D-dwarf Gliese 229b could look like. Its surface temperature is 850 Kelvin. It could be not a single, but could also be a binary brown dwarf, a binary or pair of brown dwarfs. This is called a brown dwarf desert. That's the fact that at a certain range of stars, brown dwarfs are very rare. For example, there are less than 1% G stars with a brown dwarf within 3 AU. And the reason is the migration during formation. That's why they are very rare. However, there are exceptions, like for example Ogle 25 BLG 1319 and TOI 263b. TOI means test object of interest. This overview of brown dwarfs within 65 light years of the Sun. They are closer, and that's why they are easier to detect. This is one example, Luhman 16. This is a brown dwarf binary at just 6.5 light years from Earth. One of the brown dwarfs is Luhman 16a. That's an L-type brown dwarf with 34 Jupiter masses. This in the picture is Luhman 16b. It's a T-type brown dwarf with 29 Jupiter masses at 3.5 AU distance from object A, and their orbital period is 27 years, and you can see this brown dwarf with a reddish color. This is another brown dwarf, 2-mass J222-82889-431026. This is a T-type brown dwarf, 35 light-years distance, with surface temperature 900 Kelvin. The Hubble and the Spitzer space telescopes were able to make a weather map of this brown dwarf. This is how it looks like. It has planet-sized clouds like the gas giant Jupiter, and the Spitzer Space Telescope and the Hubble Space Telescope complement each other very well, because the Spitzer can see the surface and the Hubble Space Telescope can see the inner layer. This is the light curves of this brown dwarf measured by Hubble and Spitzer at different wavelengths. And you can see phase shifts of 1.4 hours. This is the rotation period of this brown dwarf. These are cloud models for T-type brown dwarfs. At the left, you can see a mixture of forsterite, magnesium silicate plus iron. Or at the right, that's potassium chloride, water, methane, sodium sulfide, and manganese sulfide. This is an artist's impression of a gas and dust disk around a brown dwarf. Formation of planets is possible around a brown dwarf, but his life is very questionable because the habitable zone is too close to the brown dwarf. This is a JWST 1534-1043 called the Accident. This here. This is a Y-type dwarf at a 50 light-years distance. Was accidentally discovered. Its surface temperature is below 500 Kelvin. And what's special about this brown dwarf is its high velocity of over 200 kilometers per second. Has a low metallicity. So there's a relationship between metallicity and age. Low metallicity usually means it has a high age. This brown dwarf could be older than 10 billion years. Its reddish color could come from methane. There's another brown dwarf, W1906+40. It's an L dwarf at 53 light-years distance. It's smaller than Jupiter. It's just 90% of its size. Has surface storms like Jupiter and a red spot, also like Jupiter. The surface temperature is 2300 Kelvin, and this brown dwarf is known for its flare activity. This is another brown dwarf, JWST J03C6-0143. It's a binary of ultra-cool white-type brown dwarfs at 33 light-years distance. So one is about 8 to 20 Jupiter masses. The B brown dwarf is 4 to 13 Jupiter masses. So their distance is about Earth-Sun distance. Orbital period is 7 years. And the surface of these two brown dwarfs is about 300 to 400 Kelvin. There's another very interesting system, that's HIP 81208. It's a quadruple system at 477 light-years distance. It's a direct image that was made with the Very Large Telescope, VLT. Object A is a massive blue star with 2.6 solar masses. There's a companion, a brown dwarf, B, 67 Jupiter masses. At the left, this is another star. This is a red dwarf star, C. It's just 0.14 solar masses. And its companion, CB, is another brown dwarf with 15 Jupiter masses. And the system is very young at the age of just 17 million years. This is the artist's concept of Earth-like planets, potential future planets. Nowadays, the star formation rate from hydrogen gas clouds in the Milky Way is about 1 to 3 solar masses per year. But this can't go on forever, and the star formation with this mechanism by collapse of gas clouds will end in 100 trillion years in the stelliferous era of the Milkomeda galaxy. Milkomeda is the merged galaxy of Andromeda and the Milky Way. However, there is a hope. This is another binary of brown dwarfs. That's 2-mass 09392448. Another binary of T-type brown dwarfs at 17 light-years from Earth. They are at a distance of just 0.09 AU. And each of these brown dwarfs has a mass of 25 to 40 Jupiter masses. So there's another mechanism that could, in the far future, produce red dwarf tiny stars. That's the merger of heavy brown dwarfs. And the combined weight mass of the brown dwarfs must be above the limit of 80 Jupiter masses, and you will get a new red dwarf star. And there's a prediction or estimation that in the far future there could be permanently about 50 red dwarfs in the galaxy for a long time of 100 to 1000 quadrillion years. That's 10 to the 17 to 10 to the 18 years. So this is another period where at least 50 stars will be in the entire galaxy. That's why brown dwarfs could be very relevant in the far future. And that was today's video about the fascinating objects, the brown dwarfs. You can check out the links to the scientific articles. Thank you for watching. Have a nice day. Bye-bye.